Hi, this video is for the outline of Simplex Method and it's the fifth chapter of Business Decision Models. In this video, first I'll present you the essence of the Simplex Method. Then we'll solve a linear program with this method, and right after that we'll solve the same program with the Simplex tables. Simplex Method is a general procedure for solving linear programs that has two or more decision variables. Here at the left hand side of this slide we have a feasible region of a linear program, and it's drawn on a two-dimensional plane. The points of A, B, C and D are the corner points of this feasible region. Linear programs can be solved by calculating all the corner points and selecting the one with the most desirable objective value. Rather than calculating all these corner points, Simplex Method calculates a corner point if only it has a better objective value. This procedure requires less effort than a full calculation of the corner points and their objective values. Here in the middle, in the scheme, in the green boxes, we have the main steps of Simplex Method. The first step is initialization. The method begins with an arbitrary selection of any of these points. Let our initial corner point feasible be point A. The next step is determining if the corner point A is feasible or not. A corner point, let's say in here A, has neighbor corner points, corner point B and C. These are called adjacent corner points. If a corner point, here it is A, has an adjacent corner point that has a higher objective value, then it is not optimal. If the solution is not optimal, the method passes on to the next corner point and checks its optimality. This procedure is a repetitive procedure and it repeats until the procedure reaches the optimum solution. So, our Simplex Method is a repetitive process. Here at the top, given in the blue frame, we have an example linear program. To solve this with Simplex Method, first thing to do is to transform the inequalities into equations. When we look at this example linear program, we see all the constraints are inequalities. So here, to obtain the equality forms of these constraints, we add slack variables to the left side of these inequalities. Here, the equality forms of the constraints with the added slack variables are given in the middle in these equations. Now we have two more variables, and these are S1 and X2, and these also have a constraint of non-negativity. For this system of equations, basic feasible solutions can be determined by setting two of the variables to 0 and solving the equations for the remaining two. The variables that are set to 0 are called non-basic variables, and the remaining are the only variables determining the basic solution, and these are the basic variables. For the initial basic feasible solution, let x1 and x2 be the non-basic variables, then s1 and s2 become the basic variables. So we have a basic solution, a basic feasible solution. X1 and x2 are non-basic, so they have a value of 0, and we're trying to find the values for s1 and s2. And this and here at the right top side of the table of the slide, we have in the blue frame the equation form, system of equations of the linear program. Here, the next is examining the optimality of the initial solution. To do this, we need two conditions. One of them is that the coefficients of basic variables in the system of equations must equal to 1. We look at these equations and we see that each equation has a unique basic variable and they have a coefficient of 1. So the another condition which is about the equations must having a unique basic variable. So this condition is also met. That means we can check the optimality out of this system of equations. Now we're looking at the objective function, and it is the at the top of the equations, system of equations in the here. Here's the, this one. In this equation, if there's a non-basic variable with a negative coefficient, then our initial basic feasible solution is not the optimum. We know that our non-basic variables are x1 and x2, and here they have negative coefficients. So that means this basic feasible solution is not the optimum. All right. It turns out that our first basic feasible solution is not optimal. So now we can pass on to the next basic feasible solution that is adjacent to the first one. To find the neighbor basic feasible solution, we must change one of the basic variables to a non-basic variable of the initial solution and vice versa. The new basic variable is called the entering variable, and the one that becomes non-basic is called the leaving variable. When we decide these two, we have a new basic feasible solution to be tested for the optimality. Determining the entering variable is based on the rate of improvement on z. Among the non-basic alternatives, which are x1 and x2, the one that improves z the most is x1. If you remember our original form of objective function, it is z equals to 2 times x1 and plus x2. In that equation, x1 has a higher coefficient when compared to x2. That means an increase in x1 results in a higher increase in z when it's compared to x2. We can increase the value of x1 as much as the constraints allow. The constraints can be rewritten for s1 and s2. Here, given in a blue frame at the bottom, we see that the constraint equations are formed for s1 and s2. Here, s1 equals to 30 minus 5 times x1. This is the reformed. This is a reformed form of a constraint given in here. And we know that S1 and S2 cannot be negative, so this equation, the right side of this equation also cannot be negative. From here, we obtain 5 times x1 is less than or equal to 30, and therefore x1 is less than or equal to 6. Under the non-negativity constraints given in here, the maximum value of x1 can be 6. Therefore, the new value of x1 is 6. When x1 has a value of 6, here s1 drops to 0, thus becomes a non-basic variable, as we know that the variables that has a 0 value are the ones that are non-basic variables. As you remember, optimality examination requires two conditions. First, the coefficients of basic variables in the system of equations must equal to 1. In here, I'm talking for these equations given in the blue frame at the top. And the second condition, each equation must have a unique basic variable. To provide these conditions, some calculations are required. These calculations may be a multiplication of an equation by a constant other than 0, or it can be an addition of a multiple of an equation to another. Here, given in a blue frame at the bottom, we have and we have a system of equations. For this system of equations, all the calculations are done, so it is ready for the optimality check. Now we look at the first equation. It is for the objective function. The coefficients of non-basic variables here are all positive. The coefficient of x2 is 7/5, and the coefficient for s1 is 2/5, and these are both positive. Therefore, this basic feasible solution is the optimum. Here the basic variables is 6 for x1 and 18 for s2. In this system of equations, in the middle, we see that we know x2 and s1 are non-basic variables and they have a value of 0, so these two are gone, and the equation turns to the form that is the x1 is equal to 6. Similarly, these two are also gone, so s2 equals to 18, and we obtain the values of the basic variables from here as well as in the first equation. Is the z equals to 12, so the objective value of the solution is 12. In other words, in this decision we decide x to be 6 and we decide s2 to be 18, and the outcome of this decision will be 12. Once you understand the steps, the calculations of simplex method, then it is easier to understand the simplex in the tabular form. The same example can be solved on a simplex table as well. A simplex table is an alternative way of demonstration for the simplex solution. The whole procedure here is the same. Here we have a simplex table. At the first column here, we see the algebraic forms of the system of equations. This may be familiar to you because we used them in the former slides. This is the system of equations we obtained for the initial basic feasible solution. Here at the right, we have the simplex table. In the first column, it is for basic variables. Second column is for numbers of the equalities. And the remaining are for the coefficients of the basic, these are for the coefficients of the variables in the system of equations. And the rightmost column is for the right-hand side constants of the system of equations. This table is for our initial basic feasible solution, as you can remember, and this is ready for the optimality check, as each row, each equation has a unique basic variable with a coefficient 1. Among the non-basic variables, and those are x1 and x2, x1 has the smallest negative coefficient. Here, the column for x1 is called the pivot column. The next is to find the pivot row. The minimum ratio test determines the pivot row. The minimum ratio test is in the last column of this table. For each row, the ratio is the division of the right-hand side constraint by the value of the coefficient at the pivot column. This is done only for the positive coefficients at the pivot column. So here we have only a coefficient that is positive 5, and we here is the division of 30 by 5, so it's 6, and this is the only minimum ratio calculated for this table, so it's the minimum. That means the second row in here is the pivot row. In the intersection of the pivot row and the pivot column is called the pivot. By the pivot, we know that x1 here is the entering and s1 is the leaving variable. The next is to satisfy the conditions for examination of optimality of this solution. This is done by using the elementary row operations. An elementary row operation can be a multiplication of a row by a constant other than 0, or it can be an addition of a multiple of a row to another. After the elementary row operations, then the optimality can be examined by looking at the first row in here. This table is ready for the optimality check, as each row has a unique basic variable with a coefficient of 1. So we can check the optimality on the first row. Here the coefficients of non-basic variables are both positive. That means this basic feasible solution is the optimum solution. From the table, we can learn the values of the basic variables. Here it is 6 right-hand constraint in the column of right-hand constraints, 6 for x1, and the value of s2 is 18. And the objective value of this solution can be seen in the first row. It is z equals to 12. And this is the solution of simplex method in the tabular form. This is all for this video. I recommend you to read this chapter on your book to get a full grasp on these topics, and see you in the next videos. Bye.